Hello friends, welcome to the section number 54, Rolle's Theorem. Myself Soumya, Government First Aid College, Tumkur. So in this session we shall see the Rolle's Theorem. In the previous class we have studied the property of Lord box and its example. The statement of the Rolle's theorem is that if f of x is a function defined on the closed interval a comma b, then there exists f of x continuous. F of x is continuous in the closed interval a comma b. F of x is differentiable in the open interval a comma b. F of e is equal to f of b. Then there exists at least one value c of n lying definition a comma b such that f dash of c equal to 0. So the statement states that if f of x is a function defined on the closed interval a comma b, then the three condition is that f of x is continuous in the closed interval a comma b, f of x is differentiable in the open interval a comma b, and the third condition is that f of a is equal to f of b. Then there exists at least one value of c of n lying between a and b such that f dash of c is equal to. So this is the statement of the Rolle's theorem. So we shall see the proof of the Rolle's theorem. So since the function f of x is continuous in the closed interval a comma b, we can say that it is bounded in the closed interval a comma b, and it attains its bounds at least once. Therefore, we have f of c is equal to m and f of b is equal to m, where m and m are the least upper bound and the greatest lower bound of f of x in the closed interval a comma b. Now here there are two cases, either m is equal to m or capital M is not equal to small letter m. So let us see the first case. If m, so case 2, if m is not equal to m, which implies f of c is not equal to f of t, then one of them will be different from f of a and f of b. So let m is equal to f of c be different from f of a and f of b when a is less than c. It is given that f dash of c equal to limit when turning to 0 f of c plus h minus f of c divided by h. Since f of c is the greatest value of the function, therefore f of c plus h minus f of c when both h is greater than 0 and h is less than c, which is the proof of the Rolle's theorem. And the example, verify Rolle's theorem. We should see the examples on the Rolle's theorem. So verify Rolle's theorem for the function f of x is equal to x square minus 6x plus 8 in 2 comma 4 close to 2 comma 4. So given function f of x is equal to x square minus 6x plus 8 is continuous in 2 comma 4. So f dash of x is equal to 2x minus 6. That is f of x is differentiable in the closed interval 2 comma 4. These are the two conditions. Condition 1, f of x must be continuous, and the condition 2, f dash of x must be differentiable. Now the third condition is f of a must be equal to f of b. So f of a is equal to 2. So f of 2 it is equal to 4 minus 12 plus 8 and it is equal to 0. And f of b is equal to f of 4. So that is equal to 16 minus 24 plus 8 equal to 0, which implies f of a is equal to f of b. So f of x satisfies all the conditions of the Rolle's theorem, all the three conditions of the Rolle's theorem. Therefore, there exists c belongs to the open interval 2 comma 4 such that f dash of c is equal to 0. So that is 2c minus c 6 equal to 0, or 2c is equal to 6, or c is equal to 3. So we can see that 3 lies between the open interval 2 comma 4. Hence, the Rolle's theorem is verified. And the second example we shall see is that verify Rolle's theorem for f of x is equal to x square minus x minus 2 in the open interval, closed interval minus 1 comma 2. So given the function f of x as x square minus x minus 2, and we have said that it is continuous. The function is continuous in the closed interval minus 1 and 2, and f dash of x, we shall see f dash of x, we cannot differentiating the function. So 2x minus 1 will get to x minus 1. Therefore, we can say that f of x is differentiable in the open interval minus 1 comma 2. And the third condition of the Rolle's theorem is that f of a must be equal to f of b. So f of a is equal to f of minus 1, so which is equal to 1 plus 1 minus 2 equal to 0. And f of b is equal to f of 2, which is equal to 4 minus 2 minus 2, and it is equal to 0. So we have satisfied all the function satisfied all the three conditions of the Rolle's theorem. Therefore, f dash of c equal to 0 from the Rolle's theorem. So that is 2c minus 1 equal to 0, or 2c is equal to 1, or c is equal to 1 by 2. And we can see that 1 by 2 lies between minus 1 and 2. Hence, the Rolle's theorem is verified. And the third problem is that you have to verify the Rolle's theorem for the function f of x equal to sin x in the interval 0, 2 pi. So given function f of x is sin x and it is continuous in the interval 0, 2 pi. And if we see f dash of x is cos x, so we can also say that f of x is differentiable in the open interval 0, 2 pi, because we have got f dash of x is equal to cos x. So f of a, the third condition, f of a is equal to f of 0, so sin 0 is 0, and f of b is equal to f of 2 pi, sin 2 pi is also equal to 0. The third condition is also satisfied, so that is f of a is equal to f of b. Now we shall consider f dash of c equal to 0, which is equal to cos c, cos equal to 0 equal to cos pi by 2. Therefore c is equal to pi by 2, and pi by 2 belongs to 0, 2 pi. Hence the Rolle's theorem is verified. And you can solve these three problems on yourself. Verify Rolle's theorem for the function f of x is equal to x cube minus 4x in the interval minus 2, and the second problem, verify Rolle's theorem for f of x is equal to log of x square plus ab divided by x into a plus b in the closed interval a, b. The third problem, verify Rolle's theorem for f of x is equal to 2 plus x minus 1 to the power of 2 by 3 in 0, 2. And the references for this are the principles of mathematical analysis by Walter Rudin, mathematical analysis by SEM, and real analysis by NP Bani, elements of real analysis by S. Narayanan, and the Rising. Thank you.